Okay, so last lesson we learned about a Laplace transform. Now this lesson we're going to learn about inverse Laplace transform. So we're going to start with that series of shortcuts that we learned about and utilized in the last lesson. So for example, if I have a constant and I'm trying to do a inverse, that is just 1 over s. And so you can kind of see similar patterns here. E over t, e to the at, sorry, that would be the inverse Laplace of 1 over s minus a. Let's see, then you got sine of kt. If you remember from the chart last time that hyperbolic sine was underneath sine, so that's a sinth of kt. And then the cosh function is very similar to the cosine function in that it's s over s squared minus k squared. All right, so if we can recognize which general pattern we're following, then we can come back in and apply the n's and t's appropriately to figure out what the inverse is. So in this first example, we take a look at the chart, and we're looking for something that has an exponent of s. And the closest one we get is the t to the nth pattern. So I'm going to write that one out, and then let's talk through what we need to identify in our problem in order to get that to work. Okay, so first thing we'll notice is that my exponent of 5 corresponds to that n plus 1. So what does that tell me n has to be? N has to be a 4. Okay, but I don't have, so in the pattern there's an n factorial up top, but I don't have anything there, but you know, it's a constant. So just like integration rules, I can do that clever trick where I multiply by something and divide by something on the outside, and essentially I'm multiplying by 1. So I can do that in this case, and so that means I'm going to have, for my Laplace transform, I want that to say 4 factorial over s to the 4 plus 1 power, and then outside the Laplace symbol I want to have 1 over 4 factorial. And so that then would fit our pattern, and that would be t to the 4th. So 4 factorial is 24. T to the 4th. So yay. Okay, so in this next example, same trick. Look over at the chart and make a comparison as far as which one looks the closest. And so I'm looking at the sines and the cosine patterns, and this is where the s is probably going to make the biggest difference here. So if I can justify an s being up top, which in this case I have a 1, so that eliminates the cosine and the hyperbolic cosine, which means I've got to be dealing with either sine or hyperbolic sine, but hyperbolic sine has a s squared minus k squared, so that means my pattern's got to be based something off of sine. So I'm going to write out the general pattern here, and then we'll talk about how to manipulate what we have to fit this general pattern. So s squared plus k squared. Okay, so what does that tell us about k? Well, that says that k squared has to be 7, so k itself has to be the square root of 7. Okay, and then we have that issue that we don't really have, we have a number 1 up in the numerator, and I need to have k up in the numerator, so it's the same trick where I multiply by a constant, divide by a constant, and that gives me what I need. So inside the Laplace symbol, I need square root of 7 up top, and then I need s squared plus 7 in the denominator, and to balance that out, I'm going to divide by 1 over the square root of 7. And so that then fits our sine pattern pretty well. So that's 1 over the square root of 7 sine, and then our k would be square root of 7t. So there we go. All right, so next little part here is just a reminder of the linearity property. And essentially what that means is if I have a combination of functions inside the Laplace function, that I am allowed to break up the combination into individual functions and then look for patterns on it. So the inverse Laplace of alpha f of s plus beta g of s, I can take the alpha out, and then I'm just trying to figure out the inverse Laplace of f of s, and then I can take the beta out, and I'm just doing the inverse Laplace of g of s. Okay, so what does that look like in an example? Let's do one. Okay, so in this example, I can split up my fraction into two separate fractions. So let's see, and then one step at a time. So negative 2s over s squared plus 4, and then the 6 over s squared plus 4. All right, so that's kind of the first part of what the linearity property says, is that I can split this up into two separate functions. Additionally, I can factor out constants. So I can bring that negative 2 and that 6 outside. So let me do that. So we have negative 2, and that's going to give me an s over s squared plus 4. And then here I got the 6. So that's 1 over s squared plus 4. Okay, now at that point, I want to compare the patterns. You know, which patterns does this fit the closest to? So if I have an s and an s squared plus a number, that fits more like the cosine. So I'm going to write that underneath here. So the cosine kt is inverse Laplace of s over s squared plus k squared. And then the constant over s squared plus something fits the sine pattern. So sine of kt would be k over s squared plus k squared. Okay, so let's go back to our initial things. Let's look at that first pattern. So pretty clear what k is in that one. So here I got, I'll kind of highlight this. So I have a 4 here, I got a k squared there. So that tells me that k has to be 2. So that's pretty straight transformation. So that's negative 2 cosine of 2t. And the other one, so there's a 4 there, there's a 4 there. So that says that k has to be 2 as well. But up top, you notice I have a k up there, and this one I have a 1 there. Okay, well that's easily fixed. That just means I'm going to have to multiply by 2 and divide by 2. So I'm going to put a 2 here and divide a 2, and then it fits the pattern nice and pretty. So that would then be a 3 sine of 2t.